Hello and welcome back to a video series on MAC 1140 Precalculus Algebra. My name is Sean Perry. These are guided notes number 17 in the series on section 3.5, partial fraction decomposition. First, some definitions. A rational expression is a ratio of polynomials. Second of all, just like numerical fractions, if the numerator is bigger than the denominator, we call it improper. But now our notion of bigger doesn't correspond to value for the polynomial, which could take many different values. It corresponds to degree, that is to say the highest exponent of a polynomial. Now, if the degree of the numerator is greater than the degree of the denominator, we refer to this fraction as improper. Our goal is to, in the same way as we could with numbers, to use division to rewrite this as a proper fraction plus a whole number, or, in the case of rational expressions, a polynomial plus a proper rational expression. Let's see how that might look with a quick example. Let's say I had x squared over x plus 1. This would be improper because the degree of the top 2 is greater than the degree of the bottom 1. But if I carried this out using long division, making sure to put zeros in the appropriate places for my linear and constant terms respectively, we have a remainder of 1, and that tells me that this could be written as x minus 1 plus 1 over x plus 1. So this is one way that we can go from having an improper rational expression to having a polynomial plus a proper rational expression, where now the degree of the numerator is 0. And the degree of the denominator is 1. When we do partial fraction decomposition, our first goal is going to be to write an improper fraction as a proper one plus a polynomial if necessary. The following regime is going to work for proper fractions only. So our first goal is to determine if this is proper. And just looking really quickly at the exponents in the denominator, right? Imagine you FOILed this out, but only FOILed out the first terms. So we're going to wind up with 8x to the 8 on the bottom. So this is definitely proper because 3 is less than 8. Now, the idea of partial fraction decomposition is to rewrite this in terms of several proper fraction expressions. And this has some rules. The first thing we want to do is write our expression as a polynomial plus a proper rational expression if necessary. It could be that what they give us is already proper, in which case you can skip this step. If not, use long division to write it as such. In any case, you're going to want to next factor the denominator. Now, when we factor the denominator, we're going to get a series of parentheses. Each factor in the denominator will correspond to a given term in our partial fraction decomposition. There's going to be a one or more proper rational expressions over here. The number and form of these terms is going to depend on what the form of this factor looks like. But fortunately, there's only going to be 4 different cases of how that factor could look. So let's divide this into cases. Case 1, our factor looks like a linear term, ax plus b. Now, here, I make no pretense that the b could perhaps be 0, and this might just look like ax. The a could perhaps be 1, and this could just be x itself. That's entirely possible, and it would still fit this form. A and b are allowed to be any number as long as a is not equal to 0. The corresponding factor that we would want in our decomposition is going to look like a constant over ax plus b. Case 2, it looks like a linear factor, but the multiplicity is no longer 1. Let's say it's n. So if we saw something like this in the denominator, which, for example, could include x squared, amongst other things, then our corresponding factor over here that goes along with this factor on the bottom would look like a1, a constant, just a number, over ax plus b, plus, we're going to need another term, a2 over ax plus b to the 2, and we would have to keep going like this until we got all the way up to n. ax plus b to the n would go on the bottom, and then we could proceed on to consider the other factors. But we would need n terms to go along with this, what we call a repeated root. So this I would call a linear factor. This one here is a repeated linear factor. Case 3 has to do with something called an irreducible quadratic factor. We've discussed how if the discriminant in the quadratic equation is negative, we're going to have two complex roots. And those two complex roots, if we were to take and write it in their factored form and then expand that, we would get something of the form ax squared plus bx plus c, where our discriminant was negative. Now, in order to make this a general proper term in our rational decomposition, we'll have this particular one on the bottom, and on the top, we're going to need a 1 degree less polynomial. And since this is a degree 2, we're actually going to need a linear polynomial to go up top. Finally, if we have a repeated, irreducible, quadratic factor, it means that we have a quadratic irreducible which is raised to some power. And the rule for that is really just a combination of the two rules. I would need a linear factor up top, because this is a square on the bottom. And then I would need one of those for each repetition of the root that I would need. And we would repeat these all the way up to however many times the root was repeated. So anx plus bn over ax squared plus bx plus c to the nth. And then we would consider our other terms in the expansion. So let's put this into practice. I think it will seem a little bit easier once we start to actually look at how this breaks down in certain particular problems. Let's start with this one here. If I have an x for one of my factors, then x is going to be one of my denominators, and we'll need an a in the numerator as our hold place for a constant. Here I have a linear factor, and it's been repeated. So we're going to need one copy of each of those linear factors, each one raised to an increasing power all the way up to the highest power appearing in the multiplicity of this linear term. Here I have an irreducible quadratic, and this irreducible factor is going to be repeated itself. So it's going to have to appear once, x squared plus 2x plus 5, and it's going to have to appear again with a square on it, x squared plus 2x plus 5. So that's what our denominators are going to look like. And then we're going to need constants to go along with these. Linear terms only need single letters for constants, but irreducible quadratic terms need two constants. And fortunately, we're not going to be doing this one. If we were doing a problem like this, we would have to figure out what all of these are going to be. And what we're going to learn is that we can do that using a linear system of equations. So this is going to really pertain to a lot of the matrix methods and the algebra methods that you learned earlier in this section. The first thing we're going to want to do is ensure this is proper, and it is, degree 1 over degree 2. The next thing we're going to want to do is we're going to want to factor the denominator. So what we have here are two non-repeated linear factors. So what I'm going to need to do is I'm going to need to give each one its own term in the decomposition, and each one of these terms will have its own constant which goes atop. To figure out what these constants should be, we want to now clear denominators. So what's that going to look like? I won't show this step every time because once you get used to it, you're really going to see the pattern. But for now, here's the idea. If I multiply on both sides by each of these linear factors, then what I'm going to have on the left side is complete cancellation. This has gone away completely. And all that will remain is minus 2x plus 12, and that's it. On the other side, however, we're going to distribute this to both terms, and we're not going to have complete cancellation when we do. In one of these, only the x plus 4 terms are going to cancel. So 3x plus 2 remains, and it remains attached to that a. And likewise, the b, when we multiply this in, the 3x plus 2 will cancel, but x plus 4 is going to remain. So from here, there are two ways that we could proceed. I'll begin by showing the first and easiest method. This is great if there are only non-repeated linear terms. Then we can actually get away with just plugging in the roots and seeing what cancellation happens. Notice on this side, I'm going to wind up, if I say x is equal to minus 4, then the left-hand side should read as follows. And the right-hand side, well, we'll have a times 3 times minus 4 plus 2. But over here, with my b times minus 4 plus 4, that's going to go away to 0. And this is going to allow us to reduce the equation to one variable. Which variable is that? So here we have positive 8 plus 12 is 20. And on the right-hand side, that gives me a minus 10 times a. Dividing away, we wind up with negative 2 is equal to a. To solve for b, we could pick a value that turns a's term into a 0. That would be minus 2/3, its corresponding root. And if I plug that in on one side, I get the following. And if I plug this in on the right-hand side, I get where now my a term is going to 0. This gives me 40/3 is equal to 10/3 times b, and so we wind up with b is equal to 4. This lets me go back in and rewrite my coefficients, now known, and complete the decomposition. There we are. For the next one, we notice that it is indeed proper. The top doesn't factor. For the bottom, we're going to want to take out a z and take the remaining polynomial and factor it as such. These are non-repeated roots, giving me these terms in my denominators, and constants atop. Now, if I multiply on both sides by this expression, on one hand, I will cancel completely the denominator on the left-hand side, and I will get minus 2z squared minus 7z minus 2 is equal to. On the left-hand side, we'll have partial cancellation on each term. For a, that's going to give me z plus 1 times z plus 2. For b, that will cancel a z plus 1, but leave everything else. And for c, that will cancel z plus 2 and leave me a z and a z plus 1. If I now plug in z equals 0, I will kill everything except for the a term because these terms will both be 0. That's going to give me a minus 2 equal to 2 times a. This tells me that a is equal to minus 1. If I plug in z is equal to minus 1, over here I'm going to get 3. And over here, minus b. This tells me that b is equal to minus 3. And finally, if I plug in z is equal to minus 2, over here, I'm going to get 4. And for my c term, I'll have 2c. And so we find that c will be equal to positive 2. I'll record these things above in my partial fraction decomposition, which will give me negative 1, right? Negative 1 over z plus negative 3 over z plus 1 plus 2 over z plus 2. For this next one, we are proper. We begin to factor the denominator, and we're going to have 4y minus 7 over y minus 2 squared. We actually have a single repeated linear term. This is going to require a linear term over y minus 2 and another linear term over y minus 2 squared. When I clear both sides, I will have a accruing a y minus 2, because only one of them will cancel, and b will have complete cancellation. Over on my other side, I'm going to wind up with 4y minus 7 as the entire denominator cancels. Now, I could plug in y equals 2 in order to find 1 on this side and b on this side. But I couldn't exactly repeat the same thing to figure out what a is, because I would have to plug in something that makes b 0, and b doesn't have a corresponding term. So instead, what we could do is use a method called coefficient comparison. Let's recopy the equation over here, and now I'm going to distribute my a and add b to that. And notice that we have a constant term and a linear term. The rule of coefficient comparison says comparing the constant part with the constant part, the linear part with the linear part, I could, in fact, come up with these two equations. So I suggest using a sort of a tandem of the two methodologies, plugging in convenient terms when you can, and plugging in to coefficient comparison, setting up a system of equations when you run out of terms for that. This would give me a 4 over my y minus 2 and a 1 over the y minus 2 squared, which finishes this decomposition. Moving on. Okay, for this one, it is proper. We can factor the bottom pretty easily. Taking a y squared out, we have a repeated linear term and a non-repeated linear term. Let's set up our decomposition terms. We'll need 1 for a y. Y repeats up to 2, so we'll need another one. And then we're going to need something to go along with my minus 5y plus 3. If I multiply on both sides here by this denominator, on the left-hand side it cancels completely, leaving me just the numerator. And on the other side, it cancels as follows. We'll have a times a single y, since only one y cancels here, times minus 5y plus 3. And then here we're going to have b times y squared, that should be. So what the y's both cancel, and we have times minus 5y plus 3. And then over here on my c term, only the minus 5y plus 3 term cancels, and we have y squared attached to c. Here I could pick a couple easy values, like y is equal to 0, to tell me minus 6 was equal to, this one goes away, and we would just have 3 times b, so that tells me that b is minus 2. But I think rather than dealing with all of these, plugging in a root here like 3/5 into all these squares and dealing with the fractions, it's a big headache. I'm going to switch to coefficient comparison. We have minus 5ay squared plus 3ay minus 5by plus 3b plus cy squared. And if I group like terms, I'm going to have minus 5a plus c y squared plus 3a minus 5b y plus 3b. And over on the other side here, I have minus 17y squared plus 22y minus 6. Coefficient comparison says that this coefficient and this coefficient must be the same. And so I wind up with minus 5a plus c equal to minus 17. Then this one and this one must be the same, so we wind up with 3a minus 5b equal to 22. And then this last one says 3b is equal to minus 6. If we encode that as a matrix, we're going to get the following. And if we put that in reduced row echelon form by first plugging our matrix in the calculator and then taking the reduced row echelon form of that, we will wind up with the following. Note, this also gives us our b is equal to minus 2, but now also gives us a is 4 and c is 3. Thus, we get the following decomposition. This next one has two kinds of terms. This is actually an irreducible quadratic, and this is a non-repeating linear term. We'll need an ax plus b over x squared plus 5 to decompose the term corresponding to the irreducible quadratic here. And then we're going to need another constant over x plus 1 to take care of this linear term. If I multiply on both sides by this denominator, we'll clear on this side. And then on the right-hand side, the ax plus b will cancel the x squared plus 5, but x plus 1 will remain. And then correspondingly, for this c term, we're going to have the x plus 1 cancel and x squared plus 5 remains. Foiling, we would wind up with ax squared plus bx plus ax plus b plus c x squared plus 5 times c. And regrouping my like terms, we wind up with a plus c x squared plus a plus b x plus b plus 5c. And this is all equal to 13x squared minus x plus 30. So we take these coefficients and we compare them to the coefficients on the right-hand side. And that lets me write the following equations. A plus c is equal to 13. A plus b is equal to -1. And b plus 5c is equal to +3. This system can be found by taking the matrix and putting it in reduced row echelon form. So we input these values into our calculator, we take the reduced row echelon form, and if we want that in a nicer form, we could store it as fractions. So checking the answer key, this doesn't appear to be right. Let's go back and see if we can't find our error. I think I found it. Ax times -1 should in fact not be positive a here, but negative ax. That means a negative sign would have been attached here and here, which changes our matrix, and adjusting that one value appropriately, we can calculate the appropriate values. This should in fact be 6, 5, and 7 for a, b, and c respectively. So let's get those entered in for our constants. Okay, moving on. So let's look at this last one. This last one has a lot going on. It has a repeated linear term, and it has a repeated irreducible quadratic. So I'm going to wind up with, because we need every repetition up to the biggest one, and these are repeated up to squares. So we'll need 2 terms. Okay, so let's combine the fractions and look at the numerator, or clear denominators if you like, and then look at coefficient comparison. So we have, remember, if we want to envision multiplying on each side and canceling, okay, that's a long term. Let's expand everything out and collect like terms. It might help to look at this square separately. When I multiply this term by itself, I get the following expansion. And multiplying by x over here is going to increase the degree of each one of these terms by 1. If we stack things in rows, we can much more easily see what our equations are going to need to be. Because we're going to be setting these things equal to minus 7x squared minus x plus 7 and doing coefficient comparison. Now, if we don't see something like that in front, we can just assert that all of their coefficients are 0. And that gets us the following system of equations. We would write these into the corresponding matrix. We could then take this entire 6 by 7 monstrosity and plug it into our calculator. That gets us the following answers for each of the coefficients that we have in our decomposition. That would give us the following form, and we could even clean up these last two terms by dividing the 32 to the bottom. Technically, we could even probably divide a 32 out of everything, and that would be just fine. As far as why anyone would want to do this in the first place, what we are going to find when we do calculus is that things of this nature might be particularly difficult to do certain calculus operations on, namely taking an integral. However, things of this kind, we're going to be able to take the integral of these easily. So it turns out that there's a substantial difference in ease of access to the form on the right here, the decomposition form, versus the form on the left. They are equivalent, but one is easier to work with in a calculus setting. All right, that's going to do it for this video. Thank you very much for your patience and have a great day. Good luck with your studies. I'll see you in the next one.